Hello everyone, I'm Meng-Xiang. First, I would like to thank the organizer for inviting me to give this talk in Parity Violation from Hong Conference. So I'm now a CETA National Fellow at Simon Fraser University. I'm a theoretical cosmologist interested in probing fundamental physics, possibly new physics behind the cosmology and the gravitational wave observations. So today I'm going to talk about astrometric constraint on parity violation in the gravitational wave background. So my talk will mainly based on these two work with my collaborators, Santiago Jaraba, Sachiko Kuroyanagi, Qiuyue Liang, Mark Choden, and Sam Wang. Okay. So let me start from this very nice spectrum for gravitational wave. Uh, so from high frequency to low frequency. So currently we on the only evidence for gravitational wave background is coming from pulsar timing arrays in this nano hertz frequency. So this would be our focus today. So I didn't show in this diagram, but I will talk about later. The astrometry could hold the potential to detect the gravitational wave background in the similar frequency band. So, and the possible source in this frequency band would be from the astrophysical source, mainly the supermassive black hole binary in spiral, or some cosmological source from the early universe, like cosmic strings or phase transition or primitive black hole, something like that. So, before I start talking about the parity relation, oh yeah, so. Well, since this is the parity violation focused conference, I believe there will be people talking about possible parity violation signal in CMV large scale structure. So you would want to ask, are there parity violation signal in this gravitational wave background? Okay, so from theoretical point of view, uh, it's possible if you can have some parity violating gravity, for example, transcendent gravity, that will lead to the modification in both generation and propagation of gravitational waves, which will leave the parity violation signal in the GWB. And for the early universe source, even without modified gravity, you could also generate the parity violation signal in GWB via some mechanism. Um, so I list some possible model here, but I will not go into this in today's talk. Instead, I will emphasize that detecting this parity violation signal in GWB could provide a critical insight into fundamental physics. So I will focus on how can we detect this signal. Okay. So before I talk about detection for parity violation, let me briefly introduce how we detect the gravitational wave with pulsar timing arrays. So pulsar is a selector object. It rotates with very stable period. Uh, so the jet of light will swipe Earth also periodically. Once the jet is pointing toward us, you get a pulse. Okay, so you get a pulse periodically. So because of its stable period, it can use as a very precise clock. So when gravitational wave passing through, it will perturb the metric of the space-time, and therefore change the arrival time of the light from the pulse. So if you can monitor many pulsar over the whole sky, so you monitor the time residual of the arrival light, and you uh, correlate the time residual with different pulsars. In principle, you can uh, detect the gravitational wave passing through. So this is the basic idea how you detect the gravitational wave. using PTA. So similarly, you can um, in 2023, different PTA collaboration report a strong evidence like 3 to 4 sigma evidence for this Gaussian wave background. So the smoking gun is the angular correlation. So you for an isotropic background, you would expect a specific shape for the angular correlation, which is the curve shown here, so-called Handstan's curve. So this is um, smoking gun for the evidence for Gaussian wave background. So similarly, you can in principle, do this with astrometry. So the astrometry just precisely monitor the stellar position change with time. So similar to the effect here, when the Gaussian wave passing through, it will not only affect the arrival time of light, but also induce diffraction of the light. Right. So that will induce a diffraction angle of the stellar position. So similar to the positive array, so if you precisely monitor this position change and do the correlation, in principle, you can also detect the Gaussian wave. Um, uh, so now let's ask what about the parity violation? So unfortunately, for an isotropic background, PTA it cannot detect this parity violation signal. Uh, you can see from here. So for up forward left polarized Gaussian wave, it will look exactly the same as down forward right polarized Gaussian wave. So for isotropic background, you see the same amount of Gaussian wave from different direction. So you can not distinguish these two cases simply just because PTA is um, scalar map. The observable is the arrival time, which is scalar. But it's different for the astrometry because astrometry monitor a vector map. So you can look at the polarization even for an isotropic background. So you can decomposite this vector map into E mode and B mode, just similar to what we do in CMB. So um, the important thing is you can do this correlation between E mode and B mode, and this EB correlation will be non-vanishing if and only if there's a parity violating signal. Okay, so this could be a null test for the possible parity violation. So in this work with Chu Liang, Mark Jordan, and Sam Wang, we calculate the um, theoretical angular correlation shape for this EB correlation. It's just similar to this angular correlation shape expected in PTA. So if you decompose it into the spherical harmonic space, you will see, not too surprisingly, the angular correlation will dominated by the quadrupole, L equal to 2 mode, and will decay very quickly, roughly as L to the minus 6 if you go to the high L. Okay, so this will provide a smoking gun for the EB correlation signal and also connect the observable to the underlying parity violation level of the Gaussian wave background. Okay, so now you will ask, how far are we from detecting Gaussian wave background in astrometry? So the um, there's pro and con. So the shortcoming for the astrometry compared to PTA is its precision for the position monitoring is not very good for the individual star. But the advantage is we have many more stars. Okay, so roughly speaking, you can estimate the gravitational wave strain amplitude by assuming this strain amplitude is roughly the same order of the diffraction angle. Okay, so in an ideal case, we assume we can do the all sky correlation. So you can connect this strain amplitude, gravitational wave strain amplitude to the um, um, proper motion of the stars. Okay, so here I give a simple estimation using the typical Gaia parameter. Okay, so in again in ideal case, so this delta theta is the angular resolution. So um, N is the total number of source. So for Gaia survey, with much more number of source, let's say 10 to the 8 stars, compared to the PTA, we only have 50 to 60 pulsars. So you get a huge boost in the total number of source. So that will compensate the shortcoming of the precision in the angular resolution. So in ideal case, we can estimate the constraining power for collision wave is close to the nanograph signal. Okay, for Gaia stellar catalog. But again, so well, you can see this estimation. So it's comparable and roughly in the same frequency band in the ideal case. But uh, in practice, we cannot do as good as what the figure show here. So for stars, you will have an intrinsic proper motion. So that would be the big pollution to the gravitational wave signal. And also the quality of data will not be the same for each object. So so there's also another possibility to look at astrometry for quasars, not stars. So there will be some advantage for quasars. Okay, so the stellar intrinsic motion will induce EB correlation. So for example, like inside our Milky Way, the All Star will be um, rotate to the center of Milky Way. So this is just most of the star will from the Milky Way. So this is one realization of the ensemble. So even though let's say the underlying physics is pretty conserved, because we only have this one realization, you will still induce some parity variation signal from this stellar motion. Okay, but quasar could be a much better source for this EB correlation search. So the only um, only source for the large angle correlation of quasar will be induced by the cosmological large scale structure. So as we know, for the cosmological large scale structure, it's almost parity conserved. Okay, so for quasar, we can get rid of this intrinsic EB correlation, not induced from the parity violation theory. Okay, but for pulsar, in Gaia catalog, we have a smaller number length star. Okay, so but we have a better average proper motion. So so in the end, it cannot lead to a detection yet, but we can still put a constraint on that. So um, so we use the Gaia quasar catalog to provide such constraints. So this is a vector map of the selected um, catalog of the quasar. So you will see in the end we have roughly speaking 10 to the sixth number of source. So okay, so I want to emphasize that in the current Gaia DR3 data, it only provides the time average per motion data. So to detect to claim a detection of gradation wave, you need at least one cycle of gradation wave oscillation time series data to to dig out the signal. So given currently the time average promotion, we can not claim any detection of gradation wave signal. Even the data um, is better. Okay, so but instead we can also still provide an upper bound of the gradation wave amplitude for very low frequency. Okay, so for the future Gaia-DR4, they will provide the time series data. So for that data, we could have a better constraint. So for now, we just provide a bound using the current data and setting up a pipeline. And we will expect more meaningful constraint in the future. And in the same time, we also consider the VLBA data in this analysis. Okay, so the constraining on um, so the direct observable is the E mode and B mode correlation of the promotion. So since the signal is dominated by the quadrupole, so and given the quality of the current data, we only consider the L equal to 2 quadrupole mode here, and it can be connected to the pattern variation signal in the energy density. This omega is the ratio to the critical density. So it's a complex number. So the real part is the linear polarization. Uh, this U and V are Stokes parameter. So this omega U is linear polarization, which will vanish in an isotropic background. And this V is difference between the left and the right polarized gradation wave. So this omega V will encode the parity variation information, which is focus here. So using the Gaia-DR3 data, we provide this first constraint of parity variation in gradation wave background. So you will see all of these, well, of course, are consistent with zero for now. So okay, and we also provide the VLBA constraint. So interestingly, in the so you want to focus on this omega V constraint. Well, interestingly, the current VLBA will provide even better constraint compared to the Gaia-DR3. As I explained before, Gaia hasn't released its full power of the constraining. Okay, um, so now we get a constraint about 1% of the energy density compared to the critical density in our universe. And interestingly, all the central value is negative, which means the right polarization gradation wave is more than the left polarized gradation wave. But don't take this number too seriously because you know this is just very rough constraint for now. Okay. So, so I will summarize here. So the astrometry EB correlation can provide the potential parity variation signal in gradation wave background. And the quasar, in principle, would be a better source in this EB correlation search. And we provide this first astrometric constraint for now, it's just a very rough constraint, but we will expect a better and more meaningful constraint with Gaia DR4 time series proportion data. Okay, thank you.